Okay, hi, I'm going to do number 23 on page 457, and this is in section 8.5, testing a claim about a mean where sigma is not known. So in this one, it refers to a data set, but it says the data set 16, appendix B, lists the measured greenhouse gas emissions from 32 different cars. The sample has a mean of 7.78 tons and a standard deviation of 1.08 tons. So I've written up there the basic summary stats that go along with that. And the only question that I sometimes get is, why is this S as opposed to sigma? Well, the answer is it came from that sample. It came from the sample of size 32, so if you calculate things from a sample, you get sample mean, sample standard deviation. And what we're supposed to do in problem 23 is use a 0.05 significance level to test the claim that all cars have a mean greenhouse gas emission of 8 tons. Okay, so what we would do is our null hypothesis, Writer hypotheses, it's based on, we're testing about an average, so we'd have mu here as our parameter. We always want to have equality in the null, and we're testing whether it's equal to 8, I think, wasn't it? Yeah, 8. So we have mu equal 8. You have to have mu equal 8 here in the null. You can't have it the other way. And if it doesn't really specify one way or the other, we'll do mu not equal to 8. So the null is that the true average is 8, alternative is it's not. In terms of checking assumptions, we can, when n is greater than 30, a lot of times people use that as kind of the magic number. So x bar is normal, and this is because of the central limit theorem. So that's really what we are basing this on. If you have a small sample, this test may not be quite as valid. Okay, so let's calculate our test statistic. Oops. So our test statistic, this is a t-test because we have s. We don't know sigma. So our test statistic is t. It's going to be x bar minus 8 divided by s over root n. So s is 1.08 divided by the square root of 32. And so if we round this to 4 places, let's see. So I popped 8. Okay, so our t-test statistics, negative 1.1523. We'll call it negative 1.15, something like that. Okay? And so to find our p-value, remember what we're doing here is we draw out what the null distribution is. If it's a t-test, it's going to be a t null distribution. So this is not just a t, it's a t with n minus 1 degrees of freedom, so t with 31 degrees of freedom. Sometimes that's how people write that. So identify where the test statistic is, so maybe 1.15 is here, because remember, all t curves are centered at 0. And so what we're doing to find our p-value is we find all the area to the left, because this is a two-tailed test, got a not equals there, and we're going to have to double it, because the values over here in this tail are just as unusual. If you think that the mean is 8, having values over here or over here would both be equally as unusual. So we also want to find the area to the right here. And so the p-value we get, the total of those, is 0.25799, so 0.258 or so. And that's the sum of these. And again, I used the calculator to get that, but you could use StatCrunch or DDXL, or there's a number of ways you could use that you could get that. So again, what we want to do is, if alpha is 0.05, alpha sets the bar that says how unusual does our test statistic have to be in order for us to reject the null. Well, if it's a small p-value, then we're going to reject. Large p-values we fail to reject. Okay? So our p-value is up here in this fail to reject range. Okay, so because our p-value is equal to, let's say it was 0.258, which is less than which is greater than 0.05, we fail to reject. So our decision is going to be fail to reject. And to write out a conclusion, we failed to reject the null. Can't conclude that mu is different from 8. Okay. The reason we use fail reject instead of accept the null is because we really don't have any evidence that is actually equal to 8. Okay, we don't have any evidence that it's actually equal to 8. We just don't have any evidence to the contrary. So this would be the way that we'd write that. So thank you.